this video, I will be teaching you how to detect errors on a network using parity checking and two-dimensional parity checking. So, data link layer receives services from physical layer and provides services to the network layer. It happens with every layer. They are interchanging with each other, they are connected to each other. Error detection and correction is one of the functions of the data link layer, which we have already discussed. It also performs addressing, flow control, frame synchronization. So there can be two types of the errors on network. They can be single bit error and burst error. So single bit error means that only one bit has got changed, and burst error means that multiple bits have got changed. So, for example, you are trying to send 101001000 on network, and here you can see that there are some changes in red color. Okay, like 01. So these two bits have got changed. Then I have got 100 and 1001. So this bit in red color also got changed, and the bits which are written in blue color are same. So this is an example of a burst error. Parity checking is a very common method, and in the next video I'll be talking regarding this uh, C and Hamming code and advanced methods of error handling. So parity is of two types: odd parity and even parity. So parity checking cannot tell the location of the error or connect it. It can only tell that yes, an error actually exists. So parity checking will count the number of ones. An extra bit is added at the end of the data. This extra bit can be 1 or 0. And in even parity, the number of ones including the parity bit is even, and in odd parity, this number is odd. As the name suggests, even parity and odd parity. So this receiver sees the parity bit and the data, and it counts the total number of ones. So here you can see that sender is sending 011010001. So it has got total of 4 ones. So one extra one is added to maintain the parity. Because as I have already written, this is an odd parity. So here what I will do is that let us assume that receiver receives 011110001. So here you can see that there are 1 2 3 4 5 6. Total number of 6 ones are there. 6 is an even number, and it proves that the error was introduced in the network, because as I have already said that this was an odd parity. So 10 got converted into 1, and this is shown in the green color. Okay, as this one. And so if there is no change, it means that there is no error, and the same concept does apply to even parity and vice versa. The total number of ones has to be an even number in even parity. Otherwise, it is an error. So one disadvantage of this mechanism is that cannot detect errors which are involving 2-bit, 4-bit, 6-bit, 8-bit. And for example, the input data which was sent on the network was 011010000. Okay, so odd parity was used over here, and it has got 3 number of ones over here, and let us assume that 2 bits get altered on the network because of an error. So this will not get detected, as I have already told you. Because why? Okay, let us have a look at these 2 bits which got modified. They are 0111100. It has got total number of 5 ones, as you can see over here. So both 3, 5, 7, 9 are odd numbers. So another aspect is that two-dimensional parity checking was designed to solve this problem, because here we are using a table and you already know that a table has got a length and a breadth, and it can detect errors of up to 3 bits, but yes, it does have its own limitations, not more than that. See, you can use multiple error detection mechanisms also, like having code or cyclic redundancy check, but the problem is that more number of mechanisms you are using, the more slow your algorithm will become on the network. We have to save time and computing power also. So here you have got data in the form of bytes, and as you can see that let me compare the column parity. It has got even number of ones, it will be 0. It has got even number of ones, it will be 0. It has got odd number of 1. It has got uh, odd number of 1, it has got 1, the parity is 1. It has got odd number of 1, parity is 1. This has got even number of 1, parity is 0. Even number of 1, parity is 0. Odd number of 1, parity is 1. And this has got even number of 1s, so parity is 0. This has got 1, 2, 3. Odd number of 1s, parity is 1. This has got 1, 2, 3, 4. This has got even number of ones, so the parity is 0 again. Again, this has got 1, 2, 3, 4, 5 number of ones. This is an even number, so parity is 1. So here we are comparing both rows and columns. So it is very easy for a single bit to get detected in terms of rows and columns. And let us assume that there is an error. Okay. And that error is shown in the red color because 0/1, earlier it was 0, 1/0, earlier it was 1. Then I have got over here 1/0, 0/1 over here in red color, 1/0. So parity will also get changed. So in this way, the probability, I'll call it probability of detecting an error, yes, it does get increased. So checksum for error detection and correction by making use of one's complement. So in this technique, we add each word to the previous word. Okay, so the sender calculates the checksum and the receiver verifies the checksum. So for example, if you want to send say 8, 12, 13, 1 and 7, and after sending I just want to test whether the receiver has received it properly. In this kind of a situation, I will add all of them. That will be 8 plus 12 plus 13 plus 1 plus 7. This will be equal to 41, and the receiver also received the data and the checksum. And the checksum that is sent and received are same. If there are okay, so it means that there is no error. And the second way is to send the negative complement of this sum. Okay, because the negative of plus 41 will be minus 41, and if I add plus 41 and minus 41, this will be equal to 0. It means that there is no error. So error can also be detected using one's complement. Okay, so let me convert 41 into binary. This will be 101001. Okay, so let me give you a demo of it, how I have done it. And let me take 41 over here and I convert it into binary. So if I divide by 2, I get 20 over here, remainder is 1. If I divide by 2, I get 10, remainder is 0. If I divide by 2, I get 5, remainder is 0. Again, if I divide by 2, and it will be 2 and 1 and 2, 1 and 0. So this will be 1010001. And As you can see that the leftmost bits are 1 0, and I will shift them down and I will add them. So after that we get 1011, okay, and after that I find out, okay, here you are, okay, I'm adding 1001 to 10. After addition I get 1 over here, 1 over here, 10 over here. After that I find the inverse of the same. So 1011, the reverse is 0100, and in decimal number this is number 4. And already I have told you about number 41, which I did send on the network. 41 plus 4 is equal to 45. 4 is the checksum. After addition, I am getting 45, and I am converting into binary. This is equal to 101101. Binary addition already I have explained you. I don't think I have to explain it again. The leftmost bits are 10. They are added with 4 rightmost bits 1, 2, 3, 4, and it will be 1111. So, and if I okay, and the inverse of this number 1111 is 0000. So it means that there is no error on the network. And in next videos, as I've already told, I'll be talking about other mechanisms of error detection and correction. And thank you for your time.